For most of modern neuroscience, we've been listening to the brain in a very one-sided way. We've paid close attention to what neurons say when they fire electrical signals, but we've largely ignored something just as important: what neurons are hearing. Every neuron in your brain is constantly flooded with incoming messages from thousands of others. These messages arrive at tiny connection points called synapses, carried by chemical messengers, and among all of them, one stands above the rest: glutamate. It's the brain's primary excitatory neurotransmitter, and without it, thinking, learning, and memory simply wouldn't exist. The problem is that these incoming signals are extremely subtle. They're fast, faint, and easily drowned out by background activity. For years, scientists simply didn't have the tools to see them clearly in living brains. That's now changing. Researchers have engineered a new ultra-sensitive protein sensor that can detect even the weakest glutamate signals as they arrive at individual synapses. Think of it like installing a high-definition microphone inside the brain, one that can hear whispers instead of just shouts. This sensor allows scientists to watch how neurons integrate incoming information in real time. And that's a big deal, because neurons don't behave like simple switches. They act more like biological computers, weighing thousands of inputs before deciding whether to send a signal onward. That decision-making process is the foundation of everything from reflexes to creativity. By focusing on inputs rather than outputs, this technology flips the traditional approach to brain research. Instead of asking, "What did the neuron do?" scientists can now ask, "Why did it do it?" The implications go far beyond basic science. Many neurological and psychiatric disorders involve disruptions in glutamate signaling. In epilepsy, signals become overly intense. In conditions like schizophrenia or autism, the balance of excitation and inhibition can be altered. And in Alzheimer's disease, communication between neurons slowly breaks down. With this new tool, researchers can pinpoint where those breakdowns begin at the level of individual synapses. That precision could lead to earlier diagnoses, better treatments, and drugs that target the real source of the problem rather than just the symptoms. It also opens new doors for drug discovery. Instead of guessing how a treatment affects the brain, scientists can directly observe how it changes synaptic communication, moment by moment. In a deeper sense, this breakthrough brings us closer to understanding how thought itself emerges from biology. The brain isn't just firing signals randomly, it's constantly negotiating, integrating, and deciding. And now, for the first time, we can watch that process unfold. The brain has always been alive with quiet conversations. Thanks to this technology, those conversations are no longer hidden, and they may redefine how we understand the mind itself.